Hello everyone, my name is Zhichuang. Today I'm going to talk about ShadowNet, a secure and efficient on-device model inference system for convolutional neural networks. This is a joint work with Ruimin, Changming, Amrita, Long, and Somesh. So on-device machine learning is hard. On the software side, we have Android that has TensorFlow-Net support on-device machine learning. On the hardware side, smartphone vendors like Samsung, they are making new processors with AI engine and GPU to accelerate on-device model inference. For this talk, we'll focus on convolutional neural networks, or CNN, as they are one of the major types running on end devices. With on-device machine learning gets popular, the model privacy becomes an issue. Recent research have shown that it is easy for the attacker to extract models from their devices, even when they are encrypted. The existing solutions that protect on-device models can be categorized into two types. The first is crypto-based approach, but it is computationally heavy, for example, like multi-party computation and homomorphic encryption. The other solution is TEE-based. This is a promising direction. However, the major concern of running model inference inside the TEE is we will lose access to AI accelerators. Remember, the smartphone vendors are investing heavily in making AI accelerators. The other challenges, including increasing the TCP size and cannot search large applications due to the limited resource that TEE has. So the question comes, can we leverage the untrusted AI accelerators without violating model privacy? The answer is yes, ShadowNet. Here is the outline of my talk, and I will start with the security goal and threat model. Our security goal is really simple. The adversary should not learn anything extra apart from what we can learn from the querying API or the black box access model. The threat model is like this. We trust everything inside the TEE. We call it secure world. Everything outside is not trusted, including the user applications, Android OS, and remember the GPU or MPU are also in the normal world. We have three design goals. The first, we want the security to be rooted in the hardware. Second, we want to still be able to access the AI accelerators. Third, we want the game to be efficient to support real-time analysis. Our key observation is that the most computationally heavy part of CNN models are linear layers. For example, for MobileNet, 95% of the model weights and 99% of the inference time are due to the linear layers. Our key idea is we obfuscate the linear layer weights and outsource to the GPU. We restore the results back in the secure world. Only non-linear layers are also kept in the secure world. So the obfuscation of linear layers can be divided into two steps. First, we apply linear transformation to the weights. Second, we apply masks on the input. ShadowNet design also allows efficient restoration of result inside TEE. Let's take a closer look. For the linear layer weights, we apply the linear transformation. Remember, this weight transformation is only done once offline. For the input mask, we apply masks on the input for every layer during inference. And the masks are refreshed for every inference. Then the linear layers outputs are restored inside the TEE. Non-linear layers are also computed inside the TEE. Let's put it all together. For a given CNN model, for a typical convolutional layer, it usually followed by some non-linear layers. After the transformation, we apply the masks on the input in the secure world, and we outsource the input to the normal world for computation of the transformed convolutional layer, and then we restore the results back inside the TEE, and we then unmask it. and this happens for every linear layer. With this design, we achieved our first design goal. Our security is rooted in the hardware. Remember, our linear layer is now computed in the normal world, so we can leverage the untrusted AI accelerators like GPU for the computation. With this, we achieved our second design goal, access to the AI accelerators. On the performance optimization, we have two parts. On the design side, we have efficient restoration inside the TEE. We also push some computation in the offline phase. You can check our paper for more details. For the implementation optimization, we will talk more about it later. So with the optimization, we achieve our third design goal. We are efficient enough to support real-time analysis. I will hand over the implementation section to Changming.
Thanks, Zhichuang. I'll briefly talk about the implementation details of ShadowNet. So in terms of implementation, we support the most popular combinations of hardware and softwares. More specifically, we use HiKey 960 as the hardware platforms, which features Mali GPUs and ARM trust zones. And on top of that, we run Android in the normal world and OPT in the secure world. And all the AI modules are implemented in TensorFlow Lite, which is the most popular on-device machine learning module framework. And also, we did some notable optimizations for our case. For example, one notable example is that because in ShadowNet, the trusted applications and the normal application talk to each other constantly, and trusted application is not designed for such a case. So to optimize that, and for each, when execution switches between the normal world and secure world, the OPT will remap the memories every time, and which is very not necessary and costly. So we customize OPT kernel to accommodate so that we can only remap the memories of the parameters, and we preserve the memory for the weights. And this boosts up our performance significantly. And we also, when we implement the trust applications inside the TE, we have optimized memory allocations, and we use the hardware features to accelerate our computations inside the TE and the normal world, and in terms of the architecture that we support, we have ShadowNet operations to support the modules with branches. In doing that, we support a wide ranges of different architectures for machine learning modules. And we have automated model conversions, which means that if you give us a model that is implemented in TensorFlow Lite, we can just convert that automatically without any questions. And here's a link to our code, and feel free to give it a try once it's available. So with that, I hand over to Amrita to discuss the evaluation of our results.
For evaluation, we evaluated ShadowNet across 3 dimensions. First, the correctness of model inference. Second, what is the performance overhead incurred by ShadowNet? And finally, how secure is ShadowNet? We used 6 different models covering a wide variety of CNN architectures, ranging from the classic mini-VGG to the more modern complex object detection models such as YellowTiny. For correction, we measure prediction accuracy and consistency before and after ShadowNet transformation. We observed that ShadowNet's correctness is comparable to the baseline. In terms of the performance, we observed that ShadowNet incurs very low overhead, increasing the inference time by only 0.6 to 1.6 times. Additionally, the GPU acceleration can reduce the inference overhead by up to 30 milliseconds per inference. It is important to note that the performance improvement from GPUs can get only better as we use more modern and recent GPUs. Now let's look at the formal security analysis of ShadowNet. Recall that the adversary can see everything that is visible in the normal world, which is specifically the initial input and the final output of the model, the transformed weights of the linear layer, and the masked intermediate inputs. We call this the view normal. In the paper, we formalize a notion called feasible set for this view. A feasible set is basically the set of all models that could have been a valid pre-image for this view. Our guarantee states that an adversary cannot distinguish between any two models that are drawn from this feasible set. In other words, this feasible set forms a cloaking region around our private model. Now, the practical implications of this guarantee is that we conjecture that the security guarantee or the security threat here is equivalent to the black box attack setting. Stated otherwise, the adversary here has no extra advantage by observing the ShadowNet transformed models. Formally, we conjecture that the number of queries that is required to carry out an attack in the black box attack setting is roughly the same for ShadowNet. We validate our conjecture through experiments. Specifically, we carried out 2 state-of-the-art black box model stealing attacks, and we observe after the same number of queries, the attack efficacy is exactly the same for both the original model and under ShadowNet. This empirically establishes the fact that the ShadowNet transformations do not contain any useful information about the original model. Please check our paper for more details about the experimental setup. Thus, in summary, in this talk, we have established that on-device machine learning raises serious privacy concerns about the deployed model, and we have proposed a system, ShadowNet, that allows us to do secure and efficient on-device inference for convolutional neural networks. An attractive property of ShadowNet is that we are able to leverage the untrusted hardware accelerators. And ShadowNet comes with a series of design and implementation choices that make it amenable for easy adoption. Thank you for listening to our talk today, and I hope now you're triply convinced how awesome ShadowNet is, and we would be happy to take any questions.
Great talk. How does this work compare to Slalom? I remember they also have some technique to outsource linear computations to GPU.
Yeah, so Slalom only protects input privacy, but not the model weights. So our threat model is stronger. We protect model privacy.
I see. OK.
Nice talk. My question is, how about the distribution of the current numbers to steal the ShadowNet?
So here, our threat model is anything that is possible in the black box threat model, it is still possible here. So the query distribution would be literally the same for the black box API access.
Yeah, so the query number is a random number, right?
You mean what was the query distribution that we used for our attacks?
To steal the
yeah, so we'd used 2 separate, 2 attacks for our implementation. The first one, the knockoff, that actually uses an adaptive query strategy where the queries are selected adaptively using reinforcement learning, and the other one that is randomly selected.
Is this project open source, or is there any plan to go to AOSP?
We are planning to open source this project, yeah.
Yeah, is there any plan to go to AOSP?
That depends on the Android. We will propose that, right?
You will propose, okay.
Integrate with TensorFlow-lite, yeah.
Nice talk. I had a question. So in this talk, you only focus on privacy, right? So whatever work is being delegated out of the TEE to the GPU is you trust whatever result comes back. So if in your work you were to add that extra integrity guarantees, how would you go about doing that? Would that diminish all of the advantage that you get from, if you were to verify whatever comes back from the GPU inside the TEE, would that diminish all the advantages you get by offloading the work to a GPU?
I think the verification would definitely add a little bit of overhead because the verification, again, has to be done inside the TE. But my hunch would be we would still get the advantage of outsourcing it to the GPU. Like the verification, we should be able to come up with lightweight techniques to do the verification because like our transformations are like linear transformations. So the verification shouldn't be too costly.
Yeah, thank you.
All right, let's thank the speaker again. Great work.